Hello, great minds. You're welcome to another exciting moment here on this channel. And in today's lesson, we are about to prove something very disturbing to a lot of mathematicians. And it happens to be one of the most complicated arithmetic expression in math history. Of course, what I'm about to share with us, they are not entirely my ideas. They are a combination of researches I have done throughout the week and what I saw in the comment section. So I'm very certain and optimistic that if you watch this video with your open mind, at the end of the day, you're going to come up with a conclusion for 0 to the power 0, and which this video is going to address that. So let us go right into today's video and see what we can achieve before the end of the lesson. So let's get started. So we have 0 to the power 0. We want to prove 0 to the power 0, and we will start out with the concept of indices or exponent. Okay, now most people believe that 0 to the power 0 can further be expressed as 0 to the power 1 minus 1, which is true because 1 minus 1 is the same as 0. And you can further express 1 minus 1 as 0 to the power 1 upon 0 to the power 1. And this is going to give us 0 upon 0, which is undefined. This is undefined, right? Perfect. So does it mean that 0 to the power 0 is undefined? We are going to see that in a moment. Now, let us try and use this concept to prove something that we already know, which is 0 to the power 1. We know is the same as 0, right? 0 to the power 1 is 0. Even my high school student knows that 0 to the power 1 is 0. But let us see if we can use this concept to prove that. Now, I can further rewrite 0 to the power 1 as 0 to the power 2 minus 1, which can further be expressed as 0 to the power 2 upon 0 to the power 1. And this is still the same as 0 upon 0, which is still undefined. So which do we believe? Is it undefined or 0? Of course, you all know that 0 to the power 1 has to be 0. So that means this concept does not work. In fact, when you have a to the m minus n, it can be expressed as a to the m upon n, where a is not equal to 0. So that is the conclusion. So if indices cannot help us prove 0 to the power 0, then logarithm cannot do that because indices is just like the base of a logarithm, or logarithm is an extension of indices. So logarithm cannot work. Or can we have log to a base 0? Can we have that? I'm not sure we do. So log cannot work. But then let us think of something that is very close to indices, which will make a lot of sense to us. We know that 5 to the power 3 in expansion is the same as 5 times 5 times 5. And 5 to the power 2, of course, is the same as 5 times 5. And we can go further and say 5 to the power 1 is 5. So what then is 5 to the power 0? But before we do that, let us observe the pattern of the expansion for a moment. Now, from 5 cubed, which we have as 5 times 5 times 5, if I divide that by 5, that will give us 5 squared, which is 5 times 5. So if I divide that again by 5, that will give us 5, which is 5 to the power 1. So it's the progression is consistent in that order, divided by 5 to get the next sequence or the next powers of 5. So that means if I want to get 5 to the power 0, it all means that I need to divide this guy by 5, and that will give us 1. We are good with that. We know every real number to the power 0 is 1. But we are not sure about 0 to the power 0 yet. So, and again, you can also see more further to see 5 to the negative 1 is dividing 1 by 5, and that will give us 1 over 5. Now you can see this whole concept works for real numbers. Let us see if it will work with 0. Now, if we have 0 to the power 3, that is 0 times 0 times 0. If we have 0 to the power 2, that is 0 times 0. So can this give us 0 to the power 0? Of course not, because if you observe the pattern, if I decide to do the same thing we did in the real numbers example, which is 5, if I divide this guy by 0 to get the next powers of 0, it's going to give me undefined again, because I cannot divide 0 by 0. So does it mean that 0 to the power 0 is truly undefined? We cannot conclude yet until we've come to the end of this lesson. All right, let us see the graphical method. Now we're going to use a function to model something very close to 0 to the power 0. For example, if I have y is equal to x to the power 0, Okay, something close to it. If I want to graph this function, it will look more like this. This is my x-axis and this is my y-axis, right? Perfect. And let me run numbers maybe from 3 to 1 and 0, and maybe negative 1, and let's stop there. So if x is 3, for a moment, if x is 3, then we're going to have 3 to the power 0, right? Which is 1. And let's call here 1, okay? So that means this will be the point when x is 3. So when x is 2, we're going to have 2 to the power 0, which is again 1. So we are here again. And when x is 1, we have 1 to the power 0, which is 1. So we are here. So we are not sure what x will be when it is 0. We don't know what 0 to the power 0 will be. So let us keep when x is 0 and move on to the next number, which is minus 1. So when x is minus 1, of course, that's still going to give us 1. So if this function is continuous, we're going to have this drawn like this. So that implies that when x is 0, we're going to have 1. That is what it implies. But do we come to that conclusion? Not yet. Let's keep going. Let us invert this function and see what we can have if we remodel it again. So if we have something like y is equal to maybe z to the power x, for instance, and if we want to graph this function, it's going to look more like this. This is my x-axis, and this is my y-axis. And let's put values here. This is 3, this is 2, this is 1. Of course, this is 0, and we have minus 1. Let us stop there. Perfect. Let's call here 1, and maybe let's stop there. So when x is 3, we're going to have something like 0 to the power 3, which we already know is 0. So this is the point. When x is 2, we have 0 to the power 2, which is 0. When x is 1, you have 0. Then let us keep when x is 0 because we don't know what the value is yet. Let us keep that. So let us go to when x is negative 1. So when x is negative 1, that's going to look like 0 to the negative 1, which is 1 over 0, which is undefined. So we don't have values when x is negative 1. So without being biased, we cannot draw our line from this point and say it is continuous. But maybe because of this video, let's just be biased for a little and let us draw it out from this point to this point. And we kind of see that when x is 0, we may likely get 0. If we continue in that order, we may likely get 0, but we are not sure about it. It's not like so clear like this first graph. So, but let us conclude that this might give us 0. And now you see we've got 1 here and we've got 0 here, which this one is not so clear, right? But then when we get two different limits, it means that the limit does not exist, right? And does it now still mean that 0 to the power 0 is undefined? We don't have to conclude yet because we're not done with this proof. Now, this is the deal breaker. This is the last part that is going to blow your mind. I know it. So let us go to this very part. Still on function and modeling. Now, let us model something that is almost at that point when we want to prove 0 to the power 0. I mean, what I'm trying to say in essence is that if I have y is equal to x to the x, now it's almost like when we have 0 to the power 0, right? It's almost like that. So let us use this function to prove that. So what are we going to get? When x is 0, when x is 1, we're going to have 1 to the power 1. When x is 1, we're going to have 1 to the power 1, which is 1. When x is 2, we're going to have 2 to the power 2, which is 4. So if you continue in that order, this is going to diverge. I mean, this is going to diverge. But let us make it smaller. So let's say when x is 1, when x is maybe 0.5, let's just keep going in that order and let's see what we're going to get. But because of this particular function, I would like to use the Dexmos graphic calculator to show you how to go further from here. That way we're going to get it really clear. So let me move on to the Desmos graphic calculator. Yeah, this is the Desmos graphic calculator, and I'm going to use this to run that function we're talking about. So let's call it f of x. We cannot use x, we use x1 because of the rules of the Desmos here. And if you know how to use this guy, you'll find it very interesting. So let's use this one, and let's keep going. So we have this as our function, and that will be equal to, let me copy this guy. Control C, and let me plug it right here. So I have Control V, and let's close the brackets. And that is not all. Let's also put it in an exponential form. So we kind of have something like this. Yeah, we're gonna have something like this, and Control V again, Control V. Yeah, so this is what we have. And just to make it look beautiful, I think this is fine. So this is like the function y equal to x to the x, which we have in the previous class. So we kind of want to model it with the Desmos graphic calculator. So this is what we have. And now when we begin to run values for x, you're going to see the resultant. And let us create a table for that. If we create a table for this function, let's put here as x1, not x2. Sorry. Let us clean here as x1. So we kind of run values for it, x1. And let us change this one as f to the x1, because that is the result, Control C. So let's change this, guys, as this. Perfect. So when we begin to plug in different values of x here, you're going to see the resultant here for the f of x1, right? I hope it's super clear. So let me take down this stuff. Perfect. Now you can see the function. You can see how it's called, and you can see how it's moving. And you can see what is happening at this point when x is almost at 0. So let us go to when x is 1. So when x is 1, you see we have 1. That is like 1 to the 1, right? And that is this point. When x is 1, we have 1. So when x is, this is 0.1. Let's say 0.1. When x is 0.1, what do we have? We have 0.7943, like that. So it's kind of reducing because we have 1 at the very first stage. Now it's reducing. So let's go to when x is 0.2, 0.2. You see, it's reducing again. It's reducing. When x is 0.3, you see, it's going to 0.69. So at this point, you may want to conclude that this function will be convergent at the point 0. It's going to converge at 0 at this very point. But let's keep moving. Let's see when x is 0.4. You see, it's still reducing again. That means it's going to be converged at 0, right? But don't give up here. Don't just conclude here. Let's keep moving. So when x is 0.5, what do you now observe? You see, it's like there's a turning point. It's now increasing again. It's like there's a turning point at this very point right here. There's a turning point. So let's see when x is 0.7. Let's see how the graph will change. You see, it's increasing. When x is 0.7, it's increasing. So what do you then observe? When we begin to reduce 1, as 1 begins to get smaller and smaller, at some point, it was like it's converging to 0. Then at some point, it's like it turned, which, let's say, the turning point is now converging to 1. So let me make this point for x a lot smaller. Let's see what the result would be. If I select x be 0.0001, you see it's kind of converging to 1. And if we still make it a lot more smaller, let's see what that would be. You see, when x is 0.000001, what do you observe? The function is equal to 1. So this is the conclusion when x to the when z to the power 0 is being asked. I think the answer is going to be 1 from this particular stuff, because you can see when we begin to run values for x1, as x begin to reduce and begin to reduce even to the lowest form, almost close to 0, you can see that the value of 0 to the power 0 has to be 1. That is the limits case of it. So I think we can conclude that 0 to the power 0 will be 1. So guys, that is the end of today's class. If you find value from this video, if you're convinced at this point, let me know in the comment section, and let's have a wonderful day. Bye-bye and God bless.